Welcome. Today we'll be discussing section 2.5. Topics include scaling graphs, general graph transformations, as well as some examples. So for the scaling rule of a graph, we're going to have f of x equal a times some other function, we'll call it g, where there's b times x as a input. So what does this mean? Well, we're going to first restrict a and b to be positive. In other words, greater than 0. And so now what happens is a is the y stretch factor. And b is the x stretch factor. And a will make y grow or shrink proportional to whatever value it is. And b will do it, but inversely proportional, meaning that if you have a large b, it's going to kind of condense the graph. And if you have a small b, something less than 1, it'll then stretch the graph in the x direction. A has the opposite property of a large a will stretch it large in the y direction, but a small a will shrink it in the y direction. Again, small being less than 1. So how does this reflect in a standard sine wave? Well, a standard sine wave is f of x equaling a times sine of bx. So in other words, our g function here we're defining as sine. Okay, well, we're going to define a as the amplitude of f and b as the frequency of f. And so we have sine having a period of 2 pi. Well, we divide it by b, and this gets us the period of f. Again, this will showcase that if we have a b greater than 1, the period is smaller than 2 pi. So it's going to act like that we're going to shrink the intervals and the oscillation of sine. So now with the shifted sine wave, we're going to add a shift of c. We could add in a plus d here, though this just makes it shift up and down. That's not what we're interested in. We're interested for the standard sine wave on whether or not it is the period is longer or shorter, or the amplitude is higher or smaller. So these shifts, again, kind of occur how you would anticipate. This plus c will shift it to the left if positive, and it'll shift it to the right if negative. For if we have that d term, it'll shift it up if positive and shift it down if negative. And so we can see that if I was to draw some sort of function that went like this, we'll have the maximum, the absolute maximum, absolute minimum be a and negative a respectively. We're going to have a period that would be defined by this point here, or more accurately, this point to this point. This would be our period on the preferred interval. because we did one cycle. And then this phase shift is governed by C and B. Well, how can we describe this more perfectly? Well, let's do that. So the domain of the shifted standard sine wave. So we're using this function here. The domain of it is all reals. The range will go from negative A to A, as that is from the bottom of the wave to the top of the wave. We'll also see that the y-intercept, this will equal y equals A sine C. And we can simply just plug in a 0 for x. That'll annihilate the b. And so we have A times sine of whatever's left in the inside, and that'll just be C. We'll then have a x-intercept. And the x-intercept, that will occur with x is equal to pi n over b over 2b no, pi n over b minus c over b. And how this is determined is we have the phase shift, which is this negative c over b. And now we're just going to times by every interval of pi, because we hit the 0 twice in every interval. So then we can find the absolute max and absolute min. Well, the absolute max is y equals a, as denoted by the range. And this occurs at x equals, and we want to find one of them. And so we're going to say the occurrence is pi over 2b, which we'd be able to calculate that out here. And then what we want to do is subtract c over b, because this accounts for the phase shift and then how far we had to go to get to the first trough, the first peak. And then we're going to add the period to this. So that'd be 2 pi over b times n. Now I could put this n in the numerator, that's the same thing, whatever works best for you. But essentially, I'm finding one, and then I'm adding the period to find all of them. And we're going to do the same thing with the absolute minimum. We have y equals negative a, and this occurs at x equals negative pi over 2b minus c over b plus 2 pi over b times n. Again, we found a starting point, and then every other instance past that. So where is it increasing? Where is it decreasing? So if this was our minimum and this was our maximum, then how we went from our minimum to our maximum would be this first sort of increasing interval. So I'm going to write it as negative pi over 2b minus c over b. I'm going to put some space here and then have it go to pi over 2b minus c over b. And I'm going to close the bracket. Now I put a decent amount of space here, namely because this gets us the interval from this point to the peak of the graph there. Well, this interval repeats over and over and over again. So how do we do that? How do we symbolize that? Well, we're going to add the period. So 2 pi n all over b. So plus 2 pi n all over b. And we have this interval here. And so we found one interval and we added every other interval from all the other periods. Similarly, we're going to have decreasing. So let's start with this point, because we know that this point is the peak. So we have pi over 2b minus c over b. And we're going to add 2 pi n over b. Now we want to end at the next trough, which is this point, but we have to go one phase shift over. So in other words, we're going to have to add 2 pi over b to this term here, which that would give us 3 pi over 2b minus c over b, and add 2 pi n over b. Now, you could generalize this, make this into one fraction, but I like to put this into separate components because now I can see everything that's going on. So we've already talked about it a lot, but here's the period is 2 pi over b. We can also describe a preferred interval, or we'll sometimes call this the base interval. And for a preferred interval, we want to find a start. Where's the start? Well, before, for sine, our start was at this 0 when it was here at the origin. But we want to find wherever this 0 was shifted to, which is negative c over b. And then we're going to add one period, so negative c over b plus 2 pi b. We're going to exclude the interval there. Okay, the last thing we can generalize from this is whether it's even or odd. And it'd be even, or sorry, it's odd if c equals 0. Why? Because sine was an odd function, and if it doesn't shift, then we can still rotate it 180 degrees from the origin. And so we have odd, but it would be even if c is equal to pi over 2 or some sort of phase shift of pi over 2. Now, why would I have that? Well, if I was to take this and I shift this over a little bit more to where the peak was at 0, I could then have it be mirrored over the y-axis. In fact, we know this because we've seen before that sine of theta plus pi over 2 is equal to cosine of theta. So we could rewrite sine of some angle plus pi over 2 as cosine of that same angle and vice versa. This is extremely important to where this will be your check on learning for today, is to write down this equation. That'll be your check on learning for this video. That if we have a cosine graph, we could rewrite it as a sine transformation. Now, this is why we focus on the sine waves and we don't really see cosine waves, because cosine waves are just sine waves. So again, if we get this C to be a positive, sometimes we can do a little bit of trickery to make it look like something else. And we'll see an example of that later in this video. So let's find some examples of this. For example 1, let's have this function. We have f of x is equal to 3 sine of 2x plus pi over 3. So we want to describe this graph. In other words, we want the amplitude, period, phase shift, and base interval. So first we want to find, okay, and then here's our C. I waited to do this to define our C until after we get A and B to be positive. And I'll showcase this in another example. So now that we've defined our A, B, and C, we can state that our amplitude is 3. We can state that our frequency is 2. So that means our period is 2 pi over B. B is 2, so we just have pi. And so now our phase shift this is negative C over B. And something to note, if this is a positive term, then it is shifted to the left. Or sorry, it's shifted to the right, and if it's a negative term, then it's shifted to the left. That's why we include this negative here. And so how we're going to get our base interval, we want to find a starting and end point, and we're going to start with this phase shift. So first, let's define this phase shift as negative C. So that's negative pi over 3 all over B, which is 2. So we get negative pi over 6. And that's going to be our starting point for our base interval. So for base interval, we want a start point and an end point. And we're going to include the start point, exclude the end point. Our starting point is simply going to be the phase shift. So start point will be negative pi over 6. Our end point will be our start point, negative pi over 6, plus our period, which is pi. We can rewrite pi as 6 pi over 6, and combining fractions, we get 5 pi over 6. So we can say that our starting interval or base interval is negative pi over 6 to 5 pi over 6 exclusive. And that would describe everything of this graph. We can go further and find like x-intercepts, y-intercepts, but for purposes of describing the graph, this is a good starting point, and we can be more descriptive if the question entails it. So let's look at another example. So for this one, we're going to be interested in the same information. This time our f of x will be equal to negative 3 cosine of 2x. So we want it in shifted standard sine wave. This is what we want in this context. So we have to get our a sine bx plus c with a and b being positive. Well, as mentioned before, we could rewrite this as negative 3 sine of 2x plus pi over 2. As we can shift sine by pi over 2, and it will mimic a cosine. However, we have this negative 3 here. And you might be tempted going, oh, sine's an odd function. I can just throw in the negative into here. Well, we have to be at the origin to do that. We're not. And we also have to be an odd function, which we don't know since we're not at the origin. But say we were, we still wouldn't want to put the negative just into here because we need b being positive as well. So that doesn't fix our situation. So instead, what we can do is we can say, hey, I know that this negative 3, I can just shift it by half of a period, or a full period in this notation. And so I can just basically take this angle and I can subtract pi from it. And so I would get 3 sine of the same angle, 2x plus pi over 2 minus pi. I am taking this angle and I'm subtracting half of a period from it, because going from here to half a period backwards is here. My positive now became a negative, my negative now became positive. If I think of this as shifting it back half a period. Well, now that takes care of the negative. I can reduce this to get 3 sine of 2x minus pi over 2. And now this is my a, this is my b, and this is my c. So that tells me that my amplitude is 3. Nope, my amplitude was not negative 3. frequency is 2. So my period is still pi because it's 2 pi divided by b, which is 2. And my phase shift is my negative c. So I have pi over 2 divided by my b, which is 2. So my phase shift is pi over 4. Okay, now for my starting point, it will be pi over 4. My ending point for my first interval or base interval will be pi over 4 plus 1 phase shift, or sorry, plus 1 period of pi. So that would be 5 pi over 4. And then when I put them together, I'll get my base interval, which is from, this will be a bracket from pi over 4 to 5 pi over 4. Okay. Now note that we're describing a sine phase shift. If we were to plot this graph, we would have a graph that would look something like this. Where here would be 3, and here would be -3, and this occurrence would be normally at pi, but since we have a period of pi, this is now pi over 2, and we would hit a complete wave or a complete period at pi, and so we'd hit our zeros at pi over 4 and 3 pi over 4, and then here at 5 pi over 4. So we're interested in oh, sorry, I drew the positive. We're negative, so it goes like this instead. So let me erase the positive one because we had a -3 for our cosine in front of our cosine. So we have this. So now notice that I can look at this as a sine wave that starts at pi over 4 and it repeats at 5 pi over 4. This is a period of pi and an amplitude of 3. So we are able to reconstruct this cosine wave as a sine wave. And that's how we're going to talk about them from here on out. Whenever you see a cosine, think of that as a shifted sine. Okay. Thank you for watching and have a great day.